Last time we looked at the trigonometric form of complex numbers. We saw that given a complex number, a plus bi, we could express that as a point in a plane called the complex plane, where the horizontal position tells you the real part of the complex number and the vertical position tells you the imaginary part of the complex number. And we use that to describe the trigonometric form of the complex number in the following way. We can describe this point in the plane in terms of its distance from the origin, which we call r, and its angle, the angle that this segment forms with the positive x-axis, that is the angle in standard position. Now, of course, this angle is not unique. We could look at negative angles or angles that wrap around more than once, but in this situation, we say that r is the magnitude of the complex number a plus bi, which we denoted using the absolute value notation, and which has an easy formula, a squared plus e squared, and then the square root of that. And then theta is the argument, or is an argument of a plus bi. And there are a number of different ways to describe it. Because theta is not unique, we don't have precisely a formula for it, but what we do have is the relation that tangent of theta is always equal to b over a. And this can help us to find at least one argument for theta. Now, one of the major advantages of writing down the argument and the magnitude is it allows us to write down the complex number a plus bi in trigonometric form. And what this looks like is that a plus bi works out to be equal to r times cosine theta plus I sine theta, often abbreviated as r times cis theta. This is a conveniently compact notation for the complex number, but the main reason why we want to use it is because when we use this trigonometric form, multiplying complex numbers is easy. We have that if we have one complex number, not cosine, cis alpha, and this complex number is multiplied by another one, s times cis beta, then the product of these two numbers is r times s times cis of alpha plus beta. It allows us to take a multiplication of two numbers and of two complex numbers and get an expression for it that involves just multiplying two real numbers together and adding two angles together. So it simplifies the process of multiplying complex numbers significantly. And of course, any process that allows us to simplify multiplication allows us to simplify exponentiation as well. So what I want to do now is look at how we can use the trigonometric form of a complex number to get a convenient way of raising complex numbers to powers. Now, the example that I want to look at is the following. Let's find 2 minus 2i raised to the 7th power. So we've got this complex numbers raised to the 7th power. Of course, we could do this algebraically by multiplying 2 minus 2i times 2 minus 2i out a whole bunch of times 2 minus 2i. However, we don't want to do this. First of all, actually working this out would be terribly tedious. It would take a very long time and a lot of arithmetic, and potential for error is significant. Perhaps more importantly, though, this certainly won't work if the number that we're raising to is instead not 7, but 700. Then the process truly becomes infeasible to do by hand. So we want a better way of doing this. In order to figure this out, let's go ahead and see what the trigonometric form can help us with. So let's let r CIS theta be a complex number. And in fact, let's give it the notation z. And remember, this means that z is equal to r cosine theta plus r sine theta times I. So now if we want z squared, that's z times z, which gives us r CIS theta times r CIS theta, which by the formula that we had last time gives us r squared CIS times theta plus theta, which is 2 theta. All right, so that's z squared. Let's look at z cubed. Z cubed is z squared times z. Z squared we worked out before. That's r squared CIS of 2 theta times r CIS theta. And again, we know how to multiply these together. If we multiply the first number by the second, it means we're going to multiply the two coefficients in front together. So r squared times r gives us r cubed. And then we'll take CIS of, and now we have to add the two arguments together. The argument of the first number here is 2 theta. The argument of the second is theta. And so their sum is 3 theta. A pattern is starting to emerge. Let's do one more computation in order to confirm for ourselves that it's going to work. So z to the fourth is z cubed times z. We know that z cubed from the previous line is r cubed CIS 3 theta, and z is r CIS theta. And so their product will be r cubed times r, which is r to the fourth, CIS, and then 3 theta plus theta, which is 4 theta. And we can see that the pattern is continuing. Z to the fourth is r to the fourth CIS 4 theta. And the same, similar is true for z cubed, z squared, and it will continue to be the case. If we calculate z to the fifth, we'll have r to the fifth CIS 5 theta. Z to the seventh will be r to the seventh CIS 7 theta. This is the content of de Moivre's theorem. It really is an application of the product formula that we had last time. De Moivre's theorem says, given a complex number z, written as r CIS theta, and any integer n, we have that z to the n is equal to r to the n CIS n theta, which is r to the n times cosine n theta plus I times sine n theta. This gives us a formula that we can use to raise any complex number to any power we want once we have expressed it in trigonometric form. This is very helpful for lots of types of computations that we want to do. I do want to point out that this formula does also work for negative values of n and for 0. This applies when n is any integer. And so we can now use this in order to take powers of, well, pretty much any complex number we like. So let's go ahead and do that with the example that we started this slide with. So once again, let's find 2 minus 2i raised to the 7th. the first step is to express our complex number as in a trigonometric form. So the easiest way to do this is typically to graph it. Now 2 minus 2i is going to sit approximately there, below the 2 on the real axis and to the side of the negative 2i on the imaginary axis. So that means that we've got this distance here, and we've got a couple of different angles that we can look at. Let me start off by looking at this angle theta, but I'm also going to look at this angle theta prime, and we'll see what sort of a difference we get out of it. So we can write 2 minus 2i as r cis theta for some r and theta. Let's work out what those are. So the number r is the magnitude of this complex number, 2 minus 2i, which by definition is the square root of 2 squared plus negative 2 squared, which gives us the square root of 8, which we can write as 2 times the square root of 2. So there's our magnitude. And then for theta, notice that if we draw a triangle here, the two side lengths are going to be 2 and, well, negative 2 because it's going down in the negative direction. But that tells us that this theta here is a 45-degree angle, and because it's going clockwise, it's negative. So we'll say that theta is negative 45 degrees. We can use this formula just as well using degrees or radians. So we could also have said that it's negative pi over 4 radians. In fact, I'm going to go ahead and use the radians on this one just because it's going to turn out to be a little bit simpler. So now let's use this in order to calculate the 7th power of 2 minus 2i. So if we want 2 minus 2i to the 7th, that's equal to 2 times the square root of 2 times CIS of negative pi over 4 raised to the 7th. That's just changing 2 minus 2i from its rectangular form into its trigonometric form. Now we use de Moivre's theorem. And de Moivre's theorem says that when you're taking a complex number written in trigonometric form, you take the magnitude, or the coefficient, and you just raise it to whatever power you're raising the whole number to. And then you take the argument and you multiply it by the power that you're raising it to. A little bit like how when you raise something with an exponent to another exponent, you multiply the exponents together. That's basically what's going on here. So we can work this out. 2 to the 7th is 128. So we get 128 times the square root of 128 when we take the 7th power of the square root of 2. Then CIS of negative 7 pi over 4. And the only thing remaining to do is to simplify the coefficient. And so that turns out to be, let's see, 128, and then we'll be able to factor a square root of 64, which is an 8. Then 128 times 8 is 1024. So we get 1024 times the square root of 2 times CIS of negative 7 pi over 4. Now, the original problem was given to us in rectangular form. This we were given 2 minus 2i, and we're trying to find a power to it. Typically, when a problem is given to you in a form, you should give your answer back in that form. Thus, this answer, 1024 square root of 2 times CIS negative 7 pi over 4, while not incorrect, is not really the ideal solution form. We should change this back into rectangular form. So this equals 1024 square root of 2 times cosine of negative 7 pi over 4 plus I times sine of negative 7 pi over 4. Well, let's see where these things are. 7 pi over 4, or negative 7 pi over 4 rather, will be, let's see, so starting at the x-axis and moving our way around, we get negative pi over 4, negative 2 pi, negative 3 pi, negative 4 pi over 4, negative 5 pi over 4, negative 6 pi over 4, and then finally negative 7 pi over 4 out here. So here's negative 7 pi over 4. And notice that it has this a reference angle of pi over 4, and therefore cosine of negative 7 pi over 4 is just the same as cosine of pi over 4. Sine of negative 7 pi over 4 is just the same as sine of pi over 4. So we get 1024 times the square root of 2 times, now cosine of negative 7 pi over 4 will be, not negative, will be just 1 over the square root of 2, because that's cosine of pi over 4, plus I, and then sine of negative 7 pi over 4 is also 1 over the square root of 2, because that's sine of pi over 4. Distributing this through, we get 1024, because the square root of 2's cancel, plus 1024i. And so there's really the ideal form of this solution here. 1024 plus 1024i. Now, a few things to point out. First of all, we can see from this that we certainly need to go through some sort of process like this. We can't just take the 7 and apply it to the 2 and the negative 2 in the original problem. That wouldn't give us the right answer. And we can also see how efficient this method is. We can use this to compute the any power we like of any trigonometric function that we like. Now, let's see what happens if we used another angle. We used negative pi over 4 as our argument for the complex number 2 minus 2i, but it's not the only possible argument. Back originally, I mentioned I wanted to look at theta prime. Prime got covered up a little bit. Now, theta prime would be 7 pi over 4. That's the angle that starts at the positive x-axis and then winds its way around until it gets to the blue segment. So I'm just going to adjust the computation that we did here and see how that changes things. See how changing the argument inside the original expression for 2 minus 2i changes the answer. All right, so let's get rid of all of these angles that we had from before and see what happens, and hopefully we get the same thing, because the answer shouldn't depend on how we chose to write down the problem. So what if instead of negative pi over 4 we chose 7 pi over 4? That's also completely legitimate. De Moivre's theorem applies still, and then now we've got, instead of negative 7 pi over 4, we have 7 times 7 pi over 4, which gives us 49 pi over 4. But what is 49 pi over 4? Cosine of 49 pi over 4 is equal to cosine of, remember that adding 2 pi to the argument of a trigonometric function doesn't change the value of that function. So we can write cosine 49 pi over 4 is equal to cosine of pi over 4 plus 48 pi over 4. Now 48 pi over 4 is equal to 12 pi, which is, of course, 6 times 2 pi. The point of all this is that cosine of 49 pi over 4 is the same as cosine of pi over 4, because adding or subtracting any multiple of 2 pi doesn't change the value of that trigonometric function. Thus, instead of writing 49 pi over 4 inside this expression, we could write pi over 4. And there we get back to exactly the same thing that we had before. Cosine of pi over 4 is 1 over square root of 2. Sine pi over 4 is 1 over square root of 2. And we get to the same answer. So the point is, you don't need to worry about choosing the right argument for a problem like this. You can use any angle that you want that points in the right direction. Typically, choosing the smallest angle, the angle smallest in absolute value, is easier to work with. But if for some reason you really want to have a positive angle, for instance in a problem like this, then you can do that and you'll still get the same answer. So that's pretty much all there is to raising trigonometric numbers to, complex numbers in trigonometric forms to a power. Almost always, converting to a trigonometric form and using de Moivre's theorem is going to be better than multiplying it out by hand. Now, let's try going the other way. This can also help us to find roots of a complex number. So, given a real number, not real number, we want complex numbers. Given a complex number z, and we'll work with positive integers, and positive integer n, the complex number w is an nth root of z if and only if w to the n equals z. So this is similar to our definitions for roots for real numbers. Now the difference here is that when we're working with real numbers, if we take an odd root, like a cube root or a fifth root, there's only one number that will satisfy the equation. When I ask for solutions, for real solutions, I should say, to x to the fifth equals 7, well, there's only one answer to this. There's only one solution, which we write as the fifth root of 7. But when we look at even roots, like square roots and cube roots and square roots and fourth roots and so forth, then that's not the case. If I ask for the solutions to x squared equals 25, there are two solutions, 5 and negative 5. Now, by convention only, so by convention, the real square root of a number is the positive, or I should say non-negative to handle the case of 0, but is the non-negative number satisfying something like x squared equals 25. So when we write the square root of 25, that unambiguously means 5, but not for a mathematical reason, by a convention reason. We've decided that this notation, the square root of 25, means exactly 5 and not negative 5. However, using the terminology for complex roots, we can say that 5 and negative 5 are second roots of 25. Now, because we've got this this difference here, we're not going to actually use the square root notation when we talk about roots of complex numbers. We're not going to have a specific notation for it because, as it turns out, for any positive integer n and any non-zero complex number, there are n different nth roots. So no matter what number you start with, there are going to be 5 different fifth roots, 8 different eighth roots, 2 different square roots, and so forth and so on. Or I should say second roots, not square roots, because that's specific to the real numbers. So let's see how we can figure this out. It turns out that we're going to be able to describe these roots w in terms of z as long as we write everything down using, again, the trigonometric forms. So sorry about that. Let's let z be r times cosine theta plus I sine theta. And let's let w be s times cosine alpha plus I sine alpha. And we want to know what values of s and alpha will make w to the n equal z. Well, we can work out what each of these expressions are. So w to the n by De Moivre's theorem is s to the n times cosine of n alpha plus I times sine of n alpha. And so if we want w to the n to equal z, z is r times cosine theta plus I sine theta. So let's start with the magnitudes. So over here on the left side, the magnitude of w to the n is s to the n. The magnitude is always given by the coefficient that sits outside the cosine and sine terms. On the right here, the magnitude is r. If two complex numbers are the same, and we're wanting w to the n to equal z, then their magnitudes have to be the same. So that tells us that we must have that s to the n equals r. Now, because s to the n and because s and r are both real numbers, we can write that that means that s has to be the nth root of r. And furthermore, because magnitudes are positive or non-negative, we only need to take the positive root in case n happens to be even. So we're actually halfway to our answer. If w is an nth root of z, then its magnitude has to be the nth root of the magnitude of z. All right, so that's great. Let's make that happen. And once we do that, then the s to the n and r in the equation above can basically cancel. So that means that we now have that cosine of n alpha plus I times sine of n alpha has to equal cosine of theta plus I sine of theta. So because two complex numbers are equal if and only if their real parts are equal and their complex parts are equal, we have that cosine of n alpha has to equal cosine of theta, and sine of n alpha has to equal sine of theta. Now, of course, this doesn't mean that n times alpha has to equal theta, or n, because cosine is periodic, and if two angles differ by 2 pi, or a multiple of 2 pi, then they have the same cosine and they have the same sine. So the cosine of n alpha and the cosine of theta being equal, what this tells us is that n times alpha has to equal theta plus 2 pi k for some k. In other words, the angles n alpha and theta have to be coterminal with one another, but that's all they need to be. And by combining the fact that this needs to hold for cosine and for sine, this is the only possibility. The only way to have two angles that have the same sine and the same cosine is for the two angles to be coterminal. So this tells us that n alpha equals theta plus 2 pi k for some k. Since we're trying to figure out what w is, we want to know what alpha is. And so if we divide everything by n, we get that alpha is equal to theta over n plus 2 pi over n k. And I'm going to write it like that for some k, where k is an integer. All right, so what this tells us is the following. So, given that z is r times cis theta, and w is s cis alpha, what we have just computed is that w is an nth root of z if and only if s is equal to the nth root of r and alpha is equal to theta over n plus 2 pi over n plus 2 pi over nk for some integer k. So this gives us a way of checking to see whether two numbers are nth roots. Also, it gives us a way to generate them. A couple notes here. First of all, the 2 pi here can be replaced with 360 degrees. So we could also say that alpha is equal to theta over n plus 360 degrees over n times k, if we're working in degrees. Oh, sorry, that not quite correct. But the good news is we can be even more specific. Right now, it looks like we've got a lot of different possibilities for what alpha is, because k could be any integer. However, as it turns out, there's only a few different values of k that actually give different numbers. So in order to see that, let's look at basically what this sort of setup is doing. And this is a good illustration for what's going on in the problem anyway. So let's suppose that our number z sits right here. So we've got our angle theta here. And for this example, let's say that n is equal to 3. So n is equal to 3. So let's say we've got r here. Let's look at the various roots given by this w here. So when k is equal to 1, or I'm sorry, when k is equal to 0, let's start there, w will equal the nth root of r times cis of just theta over n, which in this case is 3. So that means that w is going to be the complex number whose magnitude is the nth root of r, in this case the cube root of r, and then has an argument, has an angle that's 1/3 the length of theta. So here's our first one. So this right here is theta over n, and here's our, I'll call this W0 for the W corresponding to 0. Then let's look and see, we have k equals 1. That's going to give us W1, which is the nth root of r times cis of theta over n plus 360 degrees over n times 1. So for us, that'll be the cube root of r times cis of theta over 3 plus 120 degrees, because we're doing this example with n equals 3. So let's see, what does that do? Now the angle corresponding to our second is going to be what we get by taking this angle W0 and adding 120 degrees to it. And I'm just going to estimate approximately where that is. Make that 120 degrees. Now, it's going to have the same distance, but it's going to go off like this, and there's our W1. All right, and then what about k equals 2? K equals 2 is going to give us W2, which is the cube root of r times cis of theta over 3 plus 120 degrees times 2. Now when we do that, we're going to go around another 120 degrees and get to something like this. And so our next point is down here, W2. All right, well then what about k equals 3? In this case, W3 will be the cube root of r times cis theta over 3 plus 120 degrees times 3. But now, we're right back where we started. Because 120 degrees times 3 is 360 degrees. In fact, notice that when k is n up here, then you'll always be adding 360 degrees to the theta over n piece on the left. But we already did this one. So the W3 that we just computed is the same as W0. And similarly, W1 will be the same as W4, W2 will be the same as W5, and we can keep going around and around and around again. The point is that we don't have to use all of the values of k that are possible. We actually only need to use the numbers from 0 to n minus 1, because all of the other numbers that we get are going to just be duplicates, are going to give us complex numbers that are duplicates of those n numbers. So the point of this whole exercise is the following. given a complex number z, written as r cis theta, the nth roots of z are the numbers wk, where wk is the nth root of r times cis of theta over n plus 2 pi over n, or 360 degrees over n, times k, for k equaling 0, 1, 2, up through n minus 1. So only a finite number of these complex numbers to check. Once we have this formula, computing the roots of a complex number are really just as simple as plugging them into the formula. So let's find the fifth roots of the number 32i. So by the formula above, the fifth roots of 32i are the numbers wk, which will involve the fifth root of 32. Oh, sorry, we need to, getting ahead of ourselves, the first step is to get the trigonometric form of 32i. Now, 32i is a number that lies on the imaginary axis here, and therefore it has an argument of pi over 2. So let's go ahead and do this. So that means that 32i is equal to 32, which is its magnitude, the distance from the origin, times cis of pi over 2. Therefore, the fifth roots are given by wk, which is the fifth root of 32 times cis of. Now, we've got theta over n, so that's going to be pi over 2 divided by 5, because we're taking fifth roots, plus 2 pi over 5 times k. And that's going to be for k equals 0, 1, 2, 3, and 4. So this will give us wk. So first of all, the fifth root of 32 is 2. Then we have cis of pi over 10 plus 2 pi over 5k. Now, for simplicity, it's often a good idea to simplify the expression inside the trig functions. So in this case, I'll give them a common denominator of 10 by multiplying the right-hand fraction by 2 over 2. So at this point, we get the following. So all the 2 pi k's are going to be 2 times cis pi plus 4 pi k over 10 for k equaling 1, 0, 1, 2, 3, and 4. So we can write down the fifth roots just using these numbers. So the first root is going to be 2 times cis pi over 10. W1 will be 2 cis pi plus 4 pi is 5 pi. 5 pi over 10 would be pi over 2. W2 will be 2 cis pi plus 8 pi over 10 is 9 pi over 10. W3 is 2 cis pi plus 12 pi over 10 is 13 pi over 10. And then finally W4 is 2 cis 17 pi over 10. And so this gives us trigonometric forms of the 5 roots of 32, 32i, or the 5/5 roots of 32i. We can sketch them out. They're approximately at these locations. If you do graph them out, you'll notice that the nth roots of a number always lie on a circle centered at the origin, because they all have the same magnitude, so they're all the same distance from the origin, and they are equally spaced around it, equally spaced in a number of points equal to the root that you are taking of it. Now, you can also convert these trigonometric forms into rectangular forms in our standard way. Just write it all out as 2 times cosine of, say, 9 pi over 10 plus 2 times sine of 9 pi over 10 times I. And you can put that in a calculator to approximate it, or if you do have angles that you can substitute those values in as well. All right, the last bit of terminology here is roots of unity. An nth root of unity is simply an nth root of 1. Unity is sort of an old-fashioned word meaning 1, and so pretty much the only place that we encounter this in elementary mathematics is when talking about roots of unity. And the roots of unity when working with complex numbers, are simply the roots of the number 1. Now, we're not used to thinking about 1 having non-trivial roots, because in the real numbers, any root of 1 is just 1. The square root of 1 is 1. The cube root of 1 is 1. The fourth root of 1 is 1, and so forth. But because we're dealing with complex numbers, the roots of unity are many. And there are n roots of unity for any n. Now, we can actually visualize where they are, and in fact, this is going to look sort of similar. If we consider the number 1, it's on the real axis here. First of all, the magnitude of 1 is 1, and so any nth roots of 1 are also going to have magnitude 1. That means that 1 and all of its roots of unity all lie on this circle. In fact, the unit circle. But the unit circle now sitting inside the complex plane rather than the Cartesian plane. Now, 1 is always a root of unity, because 1 raised to any power is 1, so 1 is always included in the roots of unity. But to get the others, as we looked at before, the others are going to be equally spaced out around this circle. So if we're looking for the third roots of unity, in fact, we'll go ahead and calculate them explicitly, but intuitively they're going to be approximately here and here, because that's where the 3 equally spaced points are on the unit circle, where one of the numbers is 1. So let's find the third roots of unity. We're going to follow exactly the same pattern we had before, but it's going to be even simpler because the expression for 1 is so easy. 1 is, in trigonometric form, 1 times CIS of 0. That's the angle that goes from the origin to the number 1 has a measure of 0. So that means that the third roots of 1 are given by wk, which will equal the third root of 1, which of course is just 1, times cis of 0 over 3, which is of course just 0, plus 360 degrees over 3 times k, for k equals 0, 1, and 2. Of course, this simplifies down very nicely. This gives us wk times cis of 360 degrees over 3 is 120 degrees, for k equals 0, 1, and 2. So let's actually write out what they are. If k is equal to 0, then we get w0 is equal to cis of 0, which is cosine of 0 plus I times sine of 0. Cosine of 0 is 1, sine of 0 is 0, so the one of the roots of unity that we get is just 1 itself. Now for k equals 1, we get w1, which is cis 120 degrees, which is cosine of 120 degrees plus I sine 120 degrees. Now this corresponds to the root in quadrant 2 that we've got. That's 120 degrees. And we know what the cosine and sine of this are. So this is negative square root of 3 over 2 plus 1/2 I. And similarly, we can go through the other way. If we look at W2, that's going to have an argument of 240 degrees. And when we work out the last root of unity, we get negative square root of 3 over 2 minus 1/2 I. So we see that there are actually 3 complex numbers that have the property that when you square them, or sorry, not square them, cube them, you get 1. And they are the numbers 1, negative square root of 3 over 2 plus 1/2 I, and negative square root of 3 over 2 minus 1/2 I. A good exercise if you want to practice working with complex numbers is to confirm this. Confirm that we actually have found the roots of unity of the third roots of unity by taking each of these numbers and cubing it and multiplying it all out explicitly and algebraically, doing all the calculation and cancellation and figuring out that indeed the cube of any one of these numbers does in fact get you back to 1. The nth roots of unity, it turns out, have a lot of very nice properties for us. For instance, if you consider any two roots of unity of the same order, say any 2 sixth roots of unity, and you multiply them together, you get another 6th root of unity. And so if you have a collection of nth roots of unity and you multiply any 2 of them together, you'll get another one in that list. And you can keep going around, and no matter how you multiply them together, you just get more elements in the set that you started with, the nth roots of unity. Another thing that's interesting that we haven't used here but can be used in some situations is that you can use the roots of unity in order to determine the roots of any complex number. So what I mean by that is, if I wanted to know the third roots of unity of some complex number, what I could do is just find a third root of that number and get some complex number there. And then if I took that single third root and multiplied that number by the third roots of unity, then I'd get all of the other third roots of the number that I started with. So the roots of unity are a way of getting the full complement of roots of a number if you already know 1. However, if you're just trying to compute the roots of unity to begin with, then it's easier just to use the formulas that we saw earlier.